Hello, welcome to session number 23 in the series Microwave and Millimeter Wave Circuit Design. I am Anurag Nigam, and in this session, I'm going to present to you a flow in Ptolemy simulation, right? Which is also called a discrete flow simulation, right? And in earlier session, I brought the the Ptolemy into the envelope simulation. Now in co-simulation, I'm going to take envelope into discrete flow simulation. So what you have to remember is discrete flow simulation is not timed, in a sense that it is in terms of zeros and ones, right? While the envelope simulation is timed. So you have to have an interface between these two simulations. So let's go ahead and do characterization of a single stage, right? Uh, for a modulated signal. So earlier I had shown you DQPSK. Now I'm going to create a QAM 16 source. You can create any QAM using the same method which I'm showing you. Okay, so you create a new schematic and call it as QAM 16 source. Okay, QAM 16 source. So you have it here. Now first thing, I'm going to write some equations, right? So I'm going to use this var. So in this case, first of all, most important is the bit rate. Okay, so bit rate is something which you will get, let's say from the top level simulation. So let's say bit time. Bit time is equal to 1 over bit rate. 1 divided by bit rate. Correct? So just be careful with the case, because this naming is case sensitive, right? So bit time is equal to 1 over bit rate, and then symbol time. So we are now clubbing 4 bits to form a symbol. So the symbol rate would be bit rate. So symbol rate would be equal to bit rate by 4. Bit rate by 4. Correct? And similarly, symbol time. Symbol time is going to be equal to 1 over symbol rate. Symbol rate. Okay. And then let's say samples per symbol. Samples per symbol. Okay, so let's take 10 samples per symbol. Then t step. Okay, so t step would be equal to symbol time divided by samples per symbol. Sample per symbol. Correct? And then t stop. Okay, t stop will be equal to, so for that t stop you should know how many symbols you are analyzing. So you should say total symbol. So total symbol will come from the higher level, right? So even the sample per symbol will come from the higher level, right? So what you can do is, okay, so let me just put here t stop, then I will get rid of some of the things. T stop will be equal to total symbols, total symbol multiplied by symbol time, right? Symbol time. Okay. Okay, now this sample per symbol will come from the higher level, so I can cut it out. Okay, next is I'm going to have a RF frequency, right? Just a second. So RF frequency is also to be provided, right? RF frequency. So that RF frequency will also come from the top level, and RF power will also come from the top level. So we don't have to add it, right? So we don't have to. Do we have to add it? No, we don't have to add it. Okay, so we say okay. So we are done with this. Okay, so now what I'll do is I will get a random data stream, right? So to get a random data stream, I have to go to timed sources. time sources. Okay, so I'll pick up data. Okay, so this one. So this is going to generate random data stream. So what do you have here? Okay, before even I forget that, so let's add some design parameters. So in this design parameters, you say take bit rate as the input, right? Bit rate will come from the higher level of hierarchy, and then bit rate I'll give a 76 megahertz, and unit is frequency. Okay, so that would be my bit rate. Next thing is going to be uh, samples per symbol, right? Okay, so I will have sample per symbol. So if you do a typing mistake here, you will later have to correct it. Samples per symbol, let's say 10. Default value of 10, it's a unitless number, say add. Then total number of samples, right? Total number of symbols. Okay, so let's say total number of symbol is 10,024, right? Say add. And then you have got RF FREQ. Okay, RF frequency, and that thing, let's say, is 6.5 gigahertz, and this unit is frequency, right? Okay, and then RF power would be a pure number. Let's put here 0, and let's put here unitless add. So I think we have covered total samples per symbol, total number of symbol. Okay, so in design parameters we are going to get these values here. So now T step is well defined here, T step, and then bit time. Okay, so you can put here bit time. Bit time we have 1 over bit rate. Okay, so that's bit time, and then user pattern and everything you can keep as is, and then it's going to repeat. So this is your data. Then what you do with the data is you would give it a certain what you call attenuation or gain of, let's say, 0.5. So that would come from numeric maths. uh, numeric maths Okay, so let's consider a certain gain of 0.5. Later I'll tell you why this is 0.5 there. Okay, this is because you are going to split, you are going to make a IQ, and to balance those IQ you have half the power, so I'm reducing the gain by 2. Okay, the next thing which I'm going to have is going to be a symbol splitter, right? So that will come from time data processing. Is there time data processing? Time data processing. Okay, so there is going to be a symbol splitter. That's the one. Okay, so this symbol splitter, okay, is going to divide the symbols, the bits into 2, right? So bit. Okay, once this is done, I am going to put here packing of the bin, the packing of the bits, right? So I have I and Q channel, right? So here I am going to have the symbol time will be equal to twice. Okay, and the output is going to be PAM4. Apply. Okay, so this is your symbol converter. Okay, so now we have packed 4 bits into a symbol, and I've got I and Q out of this. Then I'm going to look at a constellation. So I will go to interactive controls and displays. So it is over here, and in this case I would have TK constellation, TK slider XY plot constellation. Okay, so I'm looking at an ideal constellation right now, okay, without filtering. So I will name this as ideal const. Okay, so this is ideal constellation. correct? Okay, now here I have to put samples per symbol, which is coming from the top level. Sample per symbol, correct? And the style I want to keep as dot. Okay, so for example, last time when we talked about style, right? We have that connected in case of DQPSK. Now we are going to put dots. So we are not going to connect it, right? And persistence, I'm going to keep 100. Later I'll explain what is persistence. Okay, this is basically, the persistence is basically if a symbol has appeared as a dot, that will be there for 200 samples, right? So that is going to persist for 200 samples. Now we have kept the persistent as 100, so it is going to persist for 100 samples, right? So that's what it is. Okay. Okay, then we will filter this with a low pass filter, which is going to be a raised cosine filter. So we will put a filter here. We are going to put a filtered raised cosine. It will come from the timed filter, sorry. Where is the timed filters? So raised cosine LPF timed, right? This is the one. Okay, so in this case I am going to give it a corner frequency as the symbol rate, and excess bandwidth of only 10%, right? And it will be pulse with equalization, impulse response, and the fall would be square root, and the delay, okay, so the delay would be your filter delay. So one thing I forgot, filter length. Okay, so this is going to be a FIR filter. So in design parameters I have to add something called filter length, FILT or FLT, LENGTH. Okay, so I'm going to add that. So filter length, let's say, is 16 default value, and it's going to be a pure number, and say add. Okay, say okay. So let me just check design parameters. I have filter length here. So filter delay, so FLT delay is going to be equal to filter length by 2 into symbol time. Filter, so half, as we talked earlier, we have to have symbols halfway to the filter into symbol time, and as this is a timed raised cosine, I have to get it into a symbol time. Okay, so that is going to be filter delay. So I'll put here filter delay. Correct. So with this I am so filter line by 2, filter delay. Okay, fine. So this I am going to repeat on the other side, correct? And then I am going to connect it like this, and then this is my filtered output. So I'll put another TK plot, which would be called filtered constellation. Filtered constellation. Okay, so this filtered constellation is after filtering, and then what I'm going to do is I'm going to put this into a modulator. Okay, a QAM modulator. So this QAM modulator you'll find under timed modem. Okay, so QAM modulator, QAM modulator. Okay, so in this case So in this case, sorry with this, in this case, the carrier frequency will be RF FREQ, right? And the power level will be RF PWR, correct? And okay, so this is a dBm, so you have to do dBm to watt of something, right? And then because it's a I and Q, I have to do a minus square root of 2, right? Reference is 1, gain imbalance, phase imbalance is 0, right? So fine. So now this I'm going to give to here, and this I'm going to give to here. So once this is done, I would have to do the output. So there will be a P out. Okay. So once we are done with this, we are done with the QAM source. We are going to test it, right? So 16 minutes. Let's test this. Okay, so I'm going to make a symbol for this. So QAM source. I'll make a new symbol for this. Okay, and I like drawing, so please bear with me. Sources, snap grid. Sorry. Okay, I'm kind of drawing freak. So bear with me for a second. So it's QAM 16, so I want 16 of these. So that reminds me that this is a QAM 16. Fine, so this is a QAM 16. So that's my symbol. Close it. So now I'm going to test it. So go to new schematic and say test QAM 16. Okay, so in this case I'm going to put this one over there, test QAM 16, test source. Okay, one more thing is there. I need these numbers on this level also, right? So what I'll do is over here I'm going to create other variables also. So I'm going to start with again bit rate, right? And this is 76 megabits per second. So that's your bit rate. And then bit time is 1 over bit rate. So I'm not going to write it here. I will rather put here samples, okay, symbol rate and then symbol time, samples per symbol, sample per symbol. So that's 10, right? And total number of symbols, right? And total number of symbols, total number of symbols, that's 1024, right? Okay. And then RF frequency, that is 6.5 gigahertz, right? And then RF power, that is 0, right? And then filter length, let's say I put 32, right? And what else is there? Filter length is done. And okay, so this is there. Now I'm going to do the computation. Okay, the computation is going to be again another variable. Okay, and here I am going to put here bit time. So I'm just doing this again, 1 over bit rate, right? Okay, and then symbol rate is equal to bit rate by 4, because now we are packing 4 bits, right, into one symbol. And then symbol time is 1 over symbol rate, right? And then samples per symbol is 10, so basically then t step. So this is very simple. Symbol time divided by sample per symbol, right? And then t stop. T stop is going to be total symbol into symbol time. Total symbol into symbol time, right? So let's see if this makes sense. Bit rate, bit time, symbol rate, symbol time. Samples, total symbols 1024, total symbols into symbol time. T step is symbol time divided by sample per symbol. So where is sample per symbol? That's there. Okay, so we are ready with this, and here I'm going to just put in numbers. Bit rate and samples per symbol, and total symbols, sorry, and RF FREQ and RF power and filter length. Correct. So we are done with this. Next, I'm going to put here a, a, a resistor which comes from timed linear. So this is not the same resistor as you put from lump component. So this is because this is discrete flow simulation. So you have to go to timed linear and pick up a resistor from there. Okay, so once you're done with this, okay, now what I want to see is a spectrum. So I want to go to interactive controls and displays and put a spectrum analyzer. From sinks, sorry, it should be from sync, isn't it? Yeah, from sinks. So look for sync palette, sinks, and then I want a spectrum analyzer with resolution bandwidth. Okay, and I will call this one as, let's say, spectrum spec in. So this will be input spectrum into a PA. And do I have to change anything? Oh, I'll put a resolution bandwidth of 300 kilohertz. Window type, don't have to do anything other than just hit simulate, isn't it? So I have to put a discrete flow simulation, right? So if you go to common components, you will have a simulation controller in common components. Common components, discrete flow simulator. And in discrete flow simulator, all you have to mention is the stop time. Correct? So if everything is okay and there is no typing mistake, I should be able to see things. Okay, so now you are seeing here, this is an ideal constellation, which is 1 1, and this is also 1 1. So this is an ideal, this is a filtered constellation, and this is an ideal constellation. So basically you can see that these are fixed numbers, but they are kind of sampled, right? Because this I and Q is sampled, right? So I and Q is filtered and then sampled. So that's why they are dancing around their mean position, right? So that's your filtered constellation. So I also want to see the power level. So of course, you know, when this opened, let's put here the spectrum. So spec in. So in dBm. Okay, so this is your spectrum, which you are going to put into a PA, which is a QAM 16. Okay, another thing is I want to measure the power level. So what I'm going to do is I'm going to split here and put a 4. So just 1 second. right? So I'm going to put here a fork. So this is a fork from common components, is it? So that's going to split the signal into, without changing the power, it is going to just split the signal. And after that I want to put here TK plots, which is interactive controls and displays, and then power level. Okay, so this I am going to call input power, and right now I'm putting 0 dBm, so it should read 0. So this would be INPUT POWER. Okay, so this will be input power in dBm. Okay, then anything else I have to change here? Nothing. And I can just hit simulate. So now you are seeing 0 dBm as the input power. This is your ideal constellation, this is your filtered constellation, and you are seeing input power is almost 0 dBm, right? So fine, so we are ready with the QAM source. Now we want to put this into our PA. Okay, so what you have to do is, because PA is a circuit component, so you have to enclose this in your lower hierarchy. So you are going to make a new schematic, and I would say ENV PA. Okay, so I am going to put a envelope simulation for PA. So PA I'm going to copy from the same which we specified. So this is our PA, right? So I'm going to copy that one, and I'm going to paste it over here. So that's our PA, correct? And then I'm just going to put the pins here. So this will be P in, and then I'm going to put her P out. Okay, so this is going to be your P out. So this is as simple as that. Now, in case of your circuit, you can, again, instead of putting this behavioral, you can put your circuit which is transistorized. So in that case, you have to put your include file right here, and also your envelope simulator here. So controller for envelope simulation. So you go to simulation envelope, and in this case I am going to receive RFFREQ, right? So this will come from the top level. RFFREQ order can be as is, and T step and T stop. T step, or rather T stop, and then T step. Correct? So this is going to come from the top level. So in that case I have to create design parameters. So they are going to be RFFREQ, right? And that value I can give a default value, let's say 6.5 gigahertz, and this is a unit of frequency. So this parameter is coming from the top level hierarchy. Another parameter which is coming from top level hierarchy is T step. Okay, and that T step I am going to put, like, 1e minus 9 or by default value, and it's a unit of time, right? So this is T step, and then we have T stop, and T stop will be minus 6, let's say, microseconds, and unit of time. So we are done with this. Okay, so this T stop and T step is coming from the top level hierarchy. Okay, so I'm going to create a symbol for this one. So ENVPA, I'm going to create a symbol for this one. So new symbol, and say OK, and then just say OK. So now I am just going to replace this symbol by OK. So now I am going to just complete the symbol. Okay, so that's my PA symbol. Okay, and that symbol would come here. But notice that we are in discrete flow simulation. We have to go to the timed. So in that case, we have to tell what frequency are we going to time scale it. So we have to go to co-simulation components, right? Co-simulation components, co-simulation components, common component, co-simulation components, circuit co-simulation, ENV So we have to have this sampling done. So in this case, this frequency is RF FREQ, correct? Okay, so now this will provide a time base to that signal, and then you are going to put your PA, which is going to be envelope out. So that's your PA, right? And then similarly, you are going to come from timed back to this, right? And here I am going to put these blocks again. Okay, so this is a termination of 50 ohm. And then I'm going to put here again a spectrum analyzer and a power meter. Okay, so I am going to copy this. I'm going to keep this one over here. Okay, so now in this case, this I would call as spec out, and remaining is same. And here I will call this as output power. Output power, and this is going to be labeled as output power in dBm, correct? And I think I'm all set with this, and I'm going to hit simulate. Okay, so now I am putting in 0 and I'm getting 17.6 out, right? This is from the source. There's nothing from the output. So if you want to see the constellation at the output, you would have to first demodulate it, right? So you would have to put here a demodulator, right? So without a demodulator, you can't see the constellation, right? So what you're going to do is, right, you are going to put here a demodulator. So let me just cancel this out, and here I can plot both the spectrum out as well as spectrum in. And here you see that there is no spectral regrowth because we are at 0 dBm. As we start compressing it, we are going to see these ACPR things, adjacent channel power ratios. We will see when the power gets built in the adjacent channel, right? So okay, so now what I'm going to do is I am going to put here a demodulator, which will be coming from timed modem, and I'm going to use an external source, and I want to put a phase noise to it. So I wanted to show you two things in this setup. I want to show you EVM and all that, right? We have done ACPR, so EVM is something which I want to show you. B, I want to show you what is the effect of VCO phase noise or PLL phase noise on your demodulation. So you can see it in terms of constellation, right? So I wanted to show you that. So for that, I am going to use a demodulator with an external source. So where is the demodulator? Demodulator with the source. This is QPSK. I want to look at QAM. QAM modulator is here. QAM demodulator is here with external source. Okay, as the power is being split anyways, so we don't have to do anything. Just put here like this, and the power is split anyways. So I'm going to put here a source where I can put here the phase noise, right? So what I'm going to do here is I'm going to put here and tone. Yeah, so I have that here. Okay, so here first of all I'm going to show you this is just like a VCO, right? And we can specify here T-step, correct? Right, and then the corner frequency is your frequency is going to be RF FREQ. It will be capital F. Okay, and the power is going to be dBm to watts, or let me see how is I have mentioned power here. Okay, so it will be RF power. Okay, I can keep 0 here, 0 dBm, right? So I can put here dBm to watt, and I can say polar and then 0, and the phase 2 polar is 0 and 0. So this is your power phase is 0, additional tone 0, random phase, okay, random phase, okay, and then I can put the phase noise data. So the way you put phase noise data in this is you put your offset. So let's say 100 megahertz, and let's say it is minus 40 dBc per hertz. Then I'm going to go 1 kilohertz, and it is something like 51, minus 51. Okay, then I am going to go 10 kilohertz and minus 68 or something. Then these are all fictitious number, but when you do simulation, you can, when you simulate a VCO or a PLL, you would know these numbers exactly, right? So at 100 kilohertz, 100 kilohertz, 100 kilohertz, right? I'm going to put here 77, or yeah, or 70 or 88. It's not that bad. And then at 1 megahertz, at 1 megahertz I am going to put 98. And then at 10 megahertz, 10 megahertz I am going to put 109. Typical numbers. And that at 100 megahertz I am going to put minus 121. Okay, so this is your phase noise. So this is your signal source with the phase noise. So I'm going to demodulate that, right? And upon demodulation, okay, I am again going to put a splitter, right? So I'm going to put a splitter here. I'm going to copy the same splitter. Control C, Control V. So I'm going to have two splitters because I'm going to do two measurements. Okay, let me see how much time I have left. Already 37. I have to wrap up fast. Okay, so now here what I'm going to do is I'm going to put back the constellation, which will be demodulated constellation. So I am going to go in here and copy that. So TK plot, I'll copy this one, Control C, and come up and then say Control V. Okay, so now in this case it's going to be demodulated constellation. So I will call this as demodulated constellation. Okay, one more thing is there, the amplitude, right? Of course there is a PA, right? PA has a 17.6 dB gain here, right? So of course this will not be one cross one, right? As we are seeing constellation in 1 cross 1, we are not going to see it in 1 cross 1. So we have to add a certain amplitude, let's say 5. We can put a loss here equal to the gain of the PA, and then we'll get 1 cross 1. So we'll do that next. So now here I also want to put here TK plot. Do I want to look at power? No, I want to look at sync. So it is not under TK plot, it should be under syncs timed. Okay, I want to look at IQ signal. That's why I'm putting that here. So in this case, this is going to be Q out, correct? And then we'll copy this one over here. And this will be called I out. So I'm looking at I and Q signals, which I can give for the, so these are IQ signals. Okay, and then if I want, I can plot a I diagram. So I will put under TK plots, I diagram. Okay, so I'm going to look at I diagram, and here I'm going to put amplitude of 5 because you are going to have this as 5, right? So that's fine, I don't need to name it. Only thing I have to put here is samples per symbol, right? to put here samples per symbol. So if you do typing mistake, then you will be figuring it out for a long time. So we are done with this, and I am going to hit the persistence here is 100, right? Okay, this is going to be quite a slow simulation. Okay, so this is your ideal constellation. It will come up because it is slow, and you see the power levels haven't yet come up. Okay, so once the constellation comes in, then the power level will come up to 17.6 here with a 0 in. So right now, still not there yet because we haven't got all the symbols here. So we should have this symbol over here. We haven't got one of the symbols there, right? Okay, so persistence is something which would count that, but still I should get it, right? With the persistence of 100, I should get this. Yeah, so I should get it here also, isn't it? Yeah. So this is your ideal constellation. This is your filtered constellation. And look what is happening over here. If you see it for some time, you will see that this is the constellation, which is a demodulated constellation, but this is kind of rotating, right? You keep an eye on it. Okay, it will keep rotating. And why is it rotating? It is rotating because of the phase noise of the VCO. Okay, and you can make it faster, right? Simulation faster, and then you will be able to see this more clearly. Okay, or you can reduce the persistence on this constellation and you will see this constellation rotating. I want you to see this rotating constellation so that you have an idea of what the phase noise of a PLL will do to your received signal, right? And this is not the EVM which is coming from so whatever EVM I find out here is not just the PA, right? That error vector RMS would also have a contribution of the phase noise, right? So what we are testing here is the PA. So I will put the phase noise to 0, right? And then measure the EVM of the PA. But in a system, you will see that the RMS EVM is going to change because of the phase noise of the PLL, right? And this phase noise is not statistically predictable. That is why it cannot be corrected. So that is why we need a very good PLL in a communication system. Otherwise, our bit error rate will go up. So bit error rate is not only a function of the PA nonlinearity, it's also a function of your PLL phase noise. Okay, so you can see this constellation is kind of rotating, right? And you can see the error vector magnitude on the corners, right? So you have understood the moral of the story is in a system, it's just not the linearity of the PA. It is also going to be the phase noise which will come in. And remember that the PA which we are using is an ideal model which doesn't have the phase modulation. So it doesn't have AM PM conversion. So when you put your practical PA here, you will see more variations here, right? So this is like, optimistic result what you are seeing here. That's why it is looking so nice. But in the real systems, it's going to be much worse than what you are seeing here. Okay, and again, we are not seeing compression here because we are putting 0 dBm power, right? If we boost up the power, so we are putting in 0 here, and we are getting 17.6 out here. If you boost the power, then this you are going to see, these corners are going to go in. So we will see that in the next simulation, but let's see what's happening. So this is your eye diagram. Let's see what's happening in terms of collection of data. So it says it is collecting data and it has 1 minute 59 seconds remaining. So I am going to let it run for 1 minute 59 seconds before I interrupt it, right? Okay, so meanwhile, what more information can I give? I have to find EVM numbers, right? So what I'll do is I will go here and I will take this phase noise information. I'll just say cut. So I'm going to look at ideal source without a phase noise, and then I'm going to save it somewhere. Control V. So I'm putting it as a text so that if I want to copy paste it, I can copy paste it, right? So now this time, now the signal source which is going to use for demodulation is doesn't have a phase noise. Now you will be seeing the EVM because of the amplifier, right? So I am going to 55 seconds. So I'm going to do it without the phase noise, and that is going to be faster. And then I have to do EVM, right? So for EVM with the reference, okay, one more thing is there. I want this, okay, I want this to be -1 -1. So because there is an amplifier, right? So now the gain is 17.6. So I bring it 3 dB down on the two channels. So that's going to be -3. And then I have to do a square root for voltage. Then that would be again 3. So I have to subtract 6 from 17.6. So 11.6. So I have to put a pad of 11.6 to get this in 1 1. Okay. So let me just stop this. Data collection. Okay, 2 seconds remaining. So data collection is done. Say quit. So that's what you were seeing. Now what I was saying was I take here and I want to put a matched pad, matched loss. Okay, so that matched loss is going to be your RF power plus the gain. RF power plus the gain. The gain is going to be the 17.6 minus 6, so 11.6. Okay, so that's going to be the gain, and I am going to pad it somewhere here, right? If I pad it somewhere here, right, then I have the constellation which will be in 1 1. Okay, so now this has the gain of the PA is compensated by this pad, right? And then we'll have the constellation in -1 1 -1 1 scale. Now what I was saying, yeah, uh, yeah, so this time I have also removed the phase noise. So now it is going to be a faster simulation. So I'm going to just say simulate. Okay, so this is your ideal constellation. This is your filtered constellation. And the scale is 4 4. So let me interrupt this. Quit. Okay, quit it. Don't worry about it. Let's put the scale back to 2. Okay, and hit OK. So now you'll see ideal constellation, filtered constellation. Okay. Oh, maybe I did a mistake. Just 1 second. Oh, this is I. Sorry. Amplitude 2. Okay. Now it's okay. Simulate. Okay, so this is your ideal constellation. This is your filtered constellation. And this is more. Okay, just 1 second. Quit. And this should be 3 dB down. So this is RF power padding. Let's say it is 3 dB down, so it's 14. Still it is more, is it? Just 1 second. So there is another way. Instead of this, I can work it in terms of square root of 2. Square root of 2. Square root of 2. So don't worry. I'm just going to try out something and get this to be roughly. Square root of 2 should be the answer, right? Square root of 2 should be the answer. That much you have to shrink. Right. So anyways, let's put here some padding. Don't worry about it. So 15. Okay, wait. Quit and simulate. Ideal constellation, filtered constellation, and demodulated constellation. Okay, so I'm going to accept this. Okay, don't worry about it. Okay, so actually I'm not going to use the pad in that line. I am going to take the pad and do it for EVM. So this pad I want to put for EVM. So this is going to remain as is. So just 1 second. So this is going to remain as is. So I will put it back as 5 amplitude. And rest the circuit remains the same. Only thing I want to do is I want to take the signal out from here and pad it so that the constellation is still one cross one, right? And then I am going to go to EVM with the reference. So I'm going to do EVM with the reference. So that's your number, and in that case I just want to change this to sample per symbol. Sample per symbol, right? And then delay on the reference line I'll put -1 so that there is no delay, and here I want to put here the symbol rate, right? So the symbol rate is computed as 1/4 of the symbol rate is computed as 1/4 of the bit rate. So that's your symbol rate, right? So this EVM, this is going to measure EVM. So I am going to put the test signal over here, and the reference signal I will take from the source. So the reference signal I will take from the source. So that's my reference signal, and this is going to give me the EVM RMS, or I can put here peak standard percentile. Okay, I'll put RMS and then convert it to multiply by 100 and convert it into a percentage EVM. Okay, so now I'm ready to do the EVM simulation. So simulate this. So this is your ideal constellation, this is your filtered constellation, this is your demodulated constellation, this is your eye diagram. The power is 0 in and 17.6 out, and let's see if the data collection is done. So it is still connecting the EVM data. Okay, 10 more seconds. Okay, so done. You can see RMS EVM over here, right? So I will quit this and I will put here EVM, tabulated form, EVM result, and then I'm going to multiply this by 100. So that will give you a percentage EVM, and I will remove the intermediate. So now this is going to be 0.168% is the EVM on this. Now let us boost up the power. So when you want to boost up the power, okay, so let's put here more power. Okay, let's say we put here 10. Okay, so once we put here 10 and simulate this, ideal constellation, filtered constellation, of course this will go up, so the symbols will go out, so you won't see all 16 of them. Let's see the data collection. So this is doing the data collection. So I want to know the EVM when I have compressed it. So the EVM number after compression. So this is done. So let just 3 seconds be over. Okay. Now I'm putting out 27 dBm, right? And I say quit. So my EVM is 1.38%. And you see that these ACP numbers are going to come up. They're still very good, right? So let's put here 12. Power of 12. Correct? So we are compressing it more. Okay. So right now the compression is like 0.3 dB or something like that, right? So now we compress it by more. Okay. So I'm putting out 12, putting in 12 dBm, getting 28.6 out, right? So 12, 22 plus 7, 29.6. So it's almost 1 dB compressed, isn't it? Is data collection over? So it's done. So now I'm going to say 1 second remaining. So I'm going to say quit. So now EVM is 2.1%, right? So this is your error vector magnitude in percentage, right? And then you can see the ACP numbers. You can write here equations like we have written for the DQPSK. You can write here equation for this this QAM16, and you should be able to put your ACPRs as we have done in previous session. So in this session, we have seen one more thing I wanted to show you was, let's go here and put a large number. So we put here something like 15, and I want to see the spectrum, the constellation. Ideal constellation, filtered constellation. Oh, you still all 16 states are not covered, isn't it? So I'll put here 20. 19 seconds. 5 seconds. Almost done. Okay. So you are seeing all of them, but I want to put furthermore, quit. I want to put scale here. So I want to see the dancing constellation, my favorite. So here I'm going to put 16, and the text here, I'm going to copy that text, Control C, and put it back into phase noise data, Control V. Right, so now I have the source with the phase noise data, and then I'm going to hit simulate. So now I am going to put out, this is my ideal constellation. This is going to be my filtered constellation. And let it put out 28 point something, right? Oh, I'm going to quit this. Sorry. Let's put here 20. 20. Fine. Now say simulate. Okay, ideal constellation is over here. Filtered constellation is over here. And demodulated constellation is over here. And this is with the phase noise. Let the power build up to 28.6. Right? And you will see this constellation over here. And that constellation is going to rotate. Still the power is not built up because one symbol is missing. The average power is going to be 28.6. Okay, so you understood why this constellation is disturbed. That's the phase noise of the PLL. One symbol is missing, persistence. Okay. So uh, this being compressed, these corners would have moved in. That's all I wanted to show you. These corners are going to move in as the PA is going to compress more and more, right? So for example, let's compress it more. Quit. I want to see the constellation after compression. So let's put in here 14 dBm, right? And hit simulate. So this is your ideal. This is your filtered and this is your demodulated. Okay. So notice how the corners have moved in. You see, these corners have moved in, right? And as you compress more and more, these corners are going to move in more and more. So this is the effect of amplitude modulation, AM conversion. And the PM would be causing the rotation of the entire thing. Now there is no PM data here, right? Whatever oscillation, whatever phase rotation you are seeing is because of the phase noise of the VCO. But then the PA is also going to give you the rotation if there was a phase information in the model along the power, right? So in that case, you would have seen the rotation of the demodulated constellation also because of the PA. So I guess I have covered all the effects of a PA and a PLL on the system performance, right? I'm going to stop here. Thanks a lot. Thank you very much.